Okay, welcome back everyone, and Happy New Year to everyone. So today it's my pleasure to welcome Soufiane Hayou. We'll be talking about principled scaling of deep neural networks. Yeah, thank you, Soufiane.
Thank you, Boumediene. So hi everyone, thank you for having me. So today I'm gonna talk about how we can use some mathematics to come up with principled ways to scale deep neural networks, okay? So let us first start with defining what a deep neural network is. So you can think of a deep neural network basically as just like this, composition of layers, right? With some mappings FL. And if you do this like capital L times, you get a neural network of depth L, okay? So you can think of a residual neural network, a convolution neural network, or the simplest one, it's called the MLP, multi-layer perceptron, and this basically, or some people call it fully connected feed-forward neural network. So basically it consists of just connecting every neuron to every neuron in the next layer. Okay, so in two adjacent layers, all the neurons are connected by some weights W, and then we add the bias B and get this architecture. So this is called an MLP, right? So if you do this L times, capital L times, you get a MLP of depth L, right? So here I'm considering the case where the depth is, the width is the same for all the layers. So the width, small n. Okay, so this is like, you can think of it as a rectangular neural network. Okay. So I'm going to use this notation in all of the talk. So depth is going to be capital L. The width is small n, and the activation function is phi. Okay, so it could be ReLU, for example. Right? Feel free to interrupt me if you have any questions. Okay, so now we define this general neural architecture. Now, what happens when we increase the width or the depth or both in this neural network? So empirically, there are generally two cases. So if we do this in some principled way, I'm going to explain what principled means. We improve the performance of the model. After training, we get a better model. So if we increase the width or depth, for example, and then train the model, we improve the performance. Now, if we do this, like increase the width and depth or both in some arbitrary way, we notice a drop in performance, right? So if you want to draw this, you will see something like this. So this is your reference model, right? This dot here. Then if you increase this width or depth or both in some principled way, you see some improvements in the performance. If you do it in a arbitrary way, you see some degradation, in the performance until you reach a trivial performance, which is the performance of let's say, a random classifier in the case of a classification task, for example. Okay, right? Okay, so what do we mean by principled in arbitrary scaling, right? So just to give you some flavor of this principled versus arbitrary scaling, so I'm going to talk about initialization here. So this is an example of initialization. So here I have an MLP network that has width 300. Okay, so each layer has 300 neurons. And this network has 20 layers, okay? So a deep neural network of 20 layers, right? So here I'm showing the network outputs at initialization. So the inputs for this network are two-dimensional. They are in 0, 1 squared, and the output is one-dimensional, okay? So here I'm showing, like you can think of the X and Y axis as the inputs, and the Z axis is the output, right? So this is the network output at initialization, and the only difference between these three figures is the way we initialize the weights W in the bias B. Okay, so here I'm using a Gaussian initialization, right? With so a zero mean Gaussian initialization with some a variance sigma B for the bias and a variance sigma W scaled by some factor that we'll talk about later for the weights. Okay. So by just changing the values of the sigma B and sigma W, we obtain completely different behaviors, right? So why this is important? It's important to understand this because this has a huge impact on, for example, gradients at initialization. So you can think of the first step of gradient descent, like to train this neural network. So it will use basically the gradients as initialization. So if you have, for example, a network output that is constant, it means that this network output forgets everything about the input. So all the inputs are the same for this network. So it's not using the data, which means that the gradient here as initialization will be bad, and typically your model will not train in this case. Same thing here, you have a very unstable network output, meaning that if you change the input just a little bit, you get a completely different output. Also, the gradient here will be, unstable, and the network or the model will not be trainable in this case. So you ideally want something like this. You want the network output to be something like this, something that is well behaved. Okay, right. Also, this has an important application in Bayesian statistics. So you can think of the network as initialization as the prior in the Bayesian word, or Bayesian terms, right? So understanding what the prior looks like is very important, right? Okay. So we will not going to talk about the bias here. I'm going to just talk about initialization from now. Okay. Right. Another example of principled scaling. So here, okay, what principled means here, right? Here, principled means if you increase the width, for example, you take a very large width in depth also, you want to choose the sigma b and sigma w to have something like this, something like the third figure on the right. So I'm gonna explain this edge of chaos, chaotic phase, and order phase later when I introduce the math. Okay. Another example of principled scaling is in the case of the ResNet architecture, right? So if you have a ResNet architecture, which is basically just an architecture of this form where the mapping F can think of as a convolutional layer, or it could be also just a fully connected layer, for example. So if you increase the depth in this case, there are two cases. So if you scale the block with 1/square root of depth, and then you increase depth, in this case, we can show that the gradients are stable as you increase depth, and the features like the YL, right, are also stable. So nothing explodes with depth. Okay. If you do it with the traditional architecture without any scaling, without adding any scalar here in front of the branch, the residual branch, what you get is an exploding gradients, right? You get exploding gradients, and this, because of this, you need some engineered layers to solve this problem, and this will be typically the normalization layers like batch norm, layer norm, etc. Okay, right? So now let us define what we mean by principled scaling. So in the most general terms, you can think of a deep learning model as having all these components. So you have the initialization, you have the training algorithm. So initialization is the way you initialize the network. And then you have use some training algorithm like HGD, something to train the network, and you have also your data, right? And the architecture, of course, that depends on the hyperparameters like depth, width, activation, etc. So combining all these components give you a trained model, right? So ideally, what we mean by principled scaling is the following. So we want to tune all these components of the initialization, the training algorithm, the architecture, the data set, to maximize the performance of this trained model, okay, as we scale the width and depth, or both at the same time. Okay. Now, in reality, this is unfeasible. Why? Because it requires a complete understanding of the role of each component in this deep learning model. Okay, and we are actually far from understanding exactly the role of each component in this model, right? Right. So what do we? So you can think of this as an optimization problem, a very hard optimization problem. So you're looking for the optimal way to scale this network, to change this, to tune this components, right, in order to maximize the performance of this trained model. So it's an optimization problem in a sense, right? So, but it is very hard. So what do we do when we have a hard optimization problem? We usually come up with some relaxed approach to this optimization problem. And in this case, I'm going to talk about this idea where we focus only on two components in this model. And these components are the initialization and the architecture. So the idea is to look at what happens when you change the initialization and the architecture, right? How things evolve, like you can think of the pre-activations like this neurons or features. You can think also of the gradients, etc., and then come up with some hypothesis about how do we scale this neural network, okay, or this system in general, right? And why is this important? So, as I said before, initialization gives you a very good insights about what happens during early training, right? Because we usually start training, so HGD or any variant of HGD starts from a random initialization usually, and understanding what happens to that gradient at the early like training steps is very important, right? The other motivation is that in some cases, when you take, for example, the width of the network to infinity, we have closed form expressions. You have formulas that you can, derive some principles, some insights from theoretically, okay, and then verify them empirically. The other or the third motivation is that because the weights are random in this case, we have a lot of available tools from probability and statistic that we can use, to derive different results. Okay, so the idea here is that I'm going to look at this relaxed approach to principal scaling, where I'm going to just try to understand what happens as initialization, right? And then come up with some, not principal scaling, but principal scaling hypothesis, right? Based on this analysis. And then this hypothesis should be tested empirically, okay? This is the idea. Now, right. So now we want to understand what happens when we increase the width or depth in neural network, right? Want to understand what happens so that we can derive some principal scaling hypothesis, right? So, an interesting thing to look at is maybe try to understand what happens when we take the width to infinity or the depth to infinity or both at the same time with random weights. So this will be initialization, right? Okay. So in the case of the MLP network I introduced before, so you can think of random weights or random initialization with some Gaussian weights that have, for WL have variance sigma W squared over N and bias B sigma B squared, okay, and zero mean. So I'm initializing with zero mean. Now, why do I divide by N here? So remember, N is the width, okay? It's because I sum N terms here, right? So I have the sum of N terms. So if the variance of this thing doesn't scale as 1 over N, it will explode as N goes to infinity. So this is the first like principled scaling hypothesis, this thing, this initialization, give us, right? It tells you that if you increase the width of a neural network, you should necessarily scale the way you initialize the weight. Otherwise, things will explode, right? Because this is the first symbol. Okay? But actually, this has been, studied like extensively in the literature. And basically, for any, for general neural network architectures, MLP, ResNet, convolutional neural net, etc. So if you take the width, if you fix the depth, so this is depth fixed. So if you fix the depth and then you take the width to infinity, you can actually show that the neurons or the layer pre-activations, for example, they converge to Gaussian processes, right? Gaussian processes are basically, just you can think of like the infinite dimensional limit of a Gaussian vector as being a Gaussian process, okay? So this is a very old result, actually. So it was first proven by Radford Neal in 1994. In the case of a single layer neural network, it has been recently extended to multiple layer neural networks, okay? So the main takeaway from this is that if you increase the width of a neural network, then you should scale the variance of the initialization weights with 1 over N, okay? Right. So this is what we know about infinite width. Now, what happens for infinite or large depth L? So if we want to increase the depth. This is mainly what I'm going to talk about. But before that, we should define what we mean by infinite depth limit, right? So there are multiple notions of infinite depth limit. So you can think of the first one as taking the width to infinity first, then look at what happens when you take the depth to infinity. Okay, and there are a lot of innovations in this case, from start from the initialization, the choice of the activation function, etc., etc. And this is mainly what I'm going to talk about in this talk. Okay, there is the joint limit. This is also an interesting limit. This is a relatively new topic where basically you fix the ratio depth to width, right? And then you take them both to infinity at the same time. Okay, and see what happens in that case, right? And the third one is fixed width infinity. So here the width is fixed, and then you take depth to infinity. Okay, so these are three different notions of infinite depth. So in this talk, I will talk mainly about the first one, the infinite width then depth, and get some insights from that limit, and then talk briefly about the third one. Okay, so let's start with the first one. So infinite width then depth. So here we first take the width to infinity, then take the depth to infinity. So you can think of this as a limit that will give us some insights in the case where the width is much larger than depth, and the depth also is much larger than 1. So the depth is large, but the width is much larger. So you can think of this as like a fat network, very wide network, but also has some number of layers, capital L. Okay. Right. So from what I just said before, we know that if you take the width to infinity, because here we're interested in taking the width first to infinity, then taking the depth to infinity. So we know that if you take the width to infinity, these things, like the neurons or the pre-activations, convert to a Gaussian process, right? Okay. So a Gaussian process, basically, as I said, just can think of as a Gaussian vector, but infinite dimensional Gaussian, right? Now, the good thing is that like zero mean Gaussian distributions are fully characterized by their covariance kernel, right? QL, okay? So if they are fully characterized by this covariance kernel, then basically if we're trying to understand the large depth limit or infinite depth limit of YL at initialization, this is equivalent to understanding what happens in this limit, right? Infinite depth limit to this kernel QL, because this kernel characterizes, fully characterizes this YL, which is Gaussian in this case. Okay, right. So do you have any questions so far? Okay, so I'm just gonna feel free to interrupt me. So basically, this is the idea. So in this limit, we know that if you take the width to infinity, we have this Gaussian process behavior, then it is sufficient to understand what happens to this kernel as depth grows, if we want to understand what happens in the infinite depth limit. Okay, so the kernel can be typically decomposed into two components. So the first one is the variance components, small ql, right? And the second one is the correlations. You can think of this, the covariance between two random variables. So you can write it as the correlation multiplied by the square roots of the variance multiplied by square roots of the variance, etc. Okay, so this is the same idea. You can decompose the kernel as a variance function and then correlation kernel. Okay, so typically under some mild conditions, some technical conditions on the activation function phi, we can actually show that the variance, right? So the variance of this any input. So the variance of the neuron YL1. Okay, so why I'm considering, so here YL1 is like if you think about layer number L, layer with index L. So YL1 is like the first coordinate or the first neuron in that layer. So actually the choice of this number 1 here is arbitrary, because you can think of this as, at initialization, all the neurons have the same distribution. Okay, so you can put here any I actually instead of 1, right? So the choice of 1 is arbitrary. So basically, as I said, under some technical conditions on phi, we can show that this variance converges to a constant Q when L goes to infinity, so layer index goes to infinity, in this Q is a constant that is independent of the input. So X, remember, X is the input is the network input, okay? So meaning that for all inputs, we basically converge to the same, constant, okay? Now, the correlation kernel, which requires like, two inputs, X and X dash, understanding what happens here in the infinite depth limit, so we take L, small l to infinity, actually requires, considering like different cases of how we choose the way we the way we initialize, the variance of the initialization weights. Okay, so sigma b for the bias and sigma w for the weights. Okay, and we have actually 3 cases here. So this is the first case, what we call the ordered phase. In this case, you can show that this correlation converges to 1 exponentially quickly, right? So it's really fast. Like just after a few layers, it becomes very close to 1 correlation. Okay. So remember, this is the correlation between like the same coordinate or the same neuron in the same layer, but for different inputs, X and X dash. Okay. Right. The second case is what we call the chaotic phase. In this case, this correlation will converge to a constant C that is typically between 0 and 1. So it's different from 1, different from 0. And this converges exponentially quickly also, right? Okay. In the third case, it's called the edge of chaos. In this case, we still have convergence to 1, but it happens at a much slower rate, to the polynomial rate in this case, okay? And this alpha here will depend on, for example, on the activation function, etc. So we'll see that in the next few slides. So what does this mean? So think about this. So we have the variance that converges to a constant, right? Okay, so consider the case where like this small l is like the last layer. So small s equal to capital L. So think about the network output. So all the neurons at the last layer, they have the same variance. Okay, in the correlations, right? Depending on the way we initialize, for example, on the ordered phase, they will converge exponentially quickly to 1. So what happens here? So if you have this, 2 random variables, y L for X and y L for X dash, so they have the same variance. So think about the infinite depth. So the same variance, and they have a correlation that is equal to 1. So it means that they have the same value, right? Because if they are perfectly correlated, so correlation is equal to 1, and they have the same variance, so it means they are equal almost surely, right? So what happens in this case is that after just few layers, the network output becomes almost constant. Okay, this is why it's called ordered, because the network output will be basically the same for all the inputs. Now in the other case, the chaotic phase, this is different, and basically here it's the opposite. So think about the case where X dash is very close to X. So think about just a perturbation of X. So X dash is equal to X plus some epsilon, for example. So you have a network, the network output has the same variance for both like X and X dash, but the correlation is C, constant, independent of epsilon. So even if you take epsilon to be very small, you still have, a constant, you can think of it as a constant distance between the outputs for X and X dash, which means that the network output will be, very unstable. So it can, mathematically, we can show that the network output will be discontinuous almost everywhere, actually. Okay. For the third case, the edge of chaos, so you still have the convergence to 1, but you can expect that, let's say for the same number of layers, right? This variance, this correlation is closer. So if you initialize with the ordered phase, you are much closer to 1 compared to if you initialize with the edge of chaos, right? Which means that, the conclusion is that if you use the edge of chaos initialization, so I'm going to explain what that means. It's basically just a choice of this hyperparameters. So you kind of preserve this crucial information about the inputs. because you prevent the correlation to converge very fast to 1, okay? Because you have only a polynomial rate, right? So just to explain what do I mean by this initializations, etc. So actually the ordered phase, the chaotic phase, and the edge of chaos, you can think of them as, you know, some regions in a two-dimensional plan where the, you know, the variables are sigma b and sigma w. So if you choose sigma b, sigma w here, you get the chaotic phase, for example. This is for the hyperbolic tangent. You choose sigma b, sigma w here, you get the ordered phase. And the edge of chaos is just the curve between them. So it's like a phase transition, basically. So same thing for ILU. For ILU, there's an interesting property that the edge of chaos is reduced to a single point, actually. So in this case, you have you should initialize with sigma b equals to 0, so 0 bias, basically, and sigma w squared equal to 2, exactly to 2. And this is this coincides with the known like He initialization or K-main initialization. Okay, and this is like the, you know, this illustrates all this discussion that I've just said, and this is the figure I showed you at the beginning. So if you initialize on the ordered phase, you get this constant output. If you initialize on the chaotic phase, you get this almost like this continuous everywhere, almost everywhere kind of network output. And if you finish on the edge of chaos, you get this kind of like you know, nice shape, right? Okay, right. So now let us go to the, you know, see if this works in practice. So this is a empirical verification of this initialization hypothesis that basically tells us, well, you should initialize with the edge of chaos if you consider a deep neural network. Okay. So here I'm just showing the results for MNIST, but we have other results for different data sets. And basically the main takeaway is that, so here I'm considering a very deep neural network. So you have width 300 and depth 200. Okay, so it's a very deep neural network, 200 layers for different activation functions. And you can think, or you can see that in all cases, the edge of chaos initialization is better than the ordered phase. Well, actually, more than that, the ordered phase, with the ordered phase initialization, the model doesn't train at all. So it's stuck at the trivial, performance, right? You can make it train by adding like some solutions like Degeneracy, for example, but you still like achieve even like better performance without Degeneracy if you just initialize with edge of chaos something. Okay, right? And this is consistent like for all the, you know, the choices of the activation functions, right? Now, okay, so this is like an empirical verification of this initialization hypothesis. Now let's go a little bit further to understand like the role of the activation function. So here I'm showing you like just the graph of log 1 minus the correlation, right? So we said that the correlation converges to 1 even on the edge of chaos initialization, but it converges at a polynomial rate. So here what you can see is that indeed there is a polynomial kind of rate, so it becomes almost linear here. But with redo, you can see that that polynomial rate is larger than the polynomial rates with smooth activation functions like ILU and hyperbolic tangent. Okay, so these are like real networks, and this is a graph with like different simulations. Okay, so actually we can prove in this case that if you consider a nonlinear activation function that is sufficiently smooth, right? Then if you initialize on the edge of chaos, you can show that the correlation converges to 1 with a rate that is 1 over L, okay? While if you choose the redo activation function, or for example, leaky redo, etc., so similar activations to redo, this rate is actually 1 over L squared, right? So what does this mean? It means that if you choose a smooth activation function, it preserves the information better than redo, okay? So smooth activation functions include hyperbolic tangent, swish, ILU. There's also GLU activation function, which I think there is some recent empirical work that showed that, for example, large language models and for example, birds, etc., they perform better than better with this GLO activation function, compared to using just ReLO. So yeah, this could also explain why that happens in practice. So actually, this smoothness of the activation function preserves the information better than ReLO. Okay. So just to show an empirical verification of this hypothesis, so you can see that with ELO, for example, which is a smooth version. So ELO is this. So it's a smooth version of ReLO, right? So actually, across all like epochs, all training epochs, it performs better than ReLO. Okay, right. So here, also something to notice is that the hyperbolic tangent is also better than ReLO, right? Because it's also a smooth activation mechanism. So according to this hypothesis, it should, theoretically perform better than ReLO. But I cannot explain why, for example, ELU is better than hyperbolic tangent. So this theory doesn't explain that. Okay, could be something linked to like this gradients vanishing kind of problem with hyperbolic tangent, but that's just a conjecture, right? So now, what's the conclusion? So the conclusion is that the infinite depth limit of this, covariance kernel or correlation kernel is degenerate in all cases. So for the ordered initialization, the chaotic initialization, or the edge of chaos initialization. The only difference is that the edge of chaos initialization improves, allows training deeper networks because it preserves the information for, much deeper layers. But it will eventually also lose the information because the correlation converges to 1. So it does not solve the problem. It, mitigate that issue a little bit, but it does not solve the problem. So now the question is there a way we can avoid degeneracy, really avoid having this correlation conversion to 1, or basically which means that the covariance kernel converges to a constant kernel? Can we avoid that? Well, the question is yes, using a variant of ResNet that we call stable ResNet. So for those of you who are not familiar with ResNet, so basically a ResNet architecture, it looks like this. So you have like the layer L that is equal to a previous layer plus some scalar times a ResNet block. Okay, right. Typically, like in standard implementation, there is no scaling. And so I am introducing the scaling here. And basically what we call a stable ResNet is any ResNet such that if you sum these scaling factors, like the squares of these scaling factors, and you take the supremum over L, so you can think of L going to infinity, then this remains bounded. Okay. So if this scaling factors satisfy this property, then I call this network a stable ResNet. Okay. Why? So why do I use this property? Why do I need this stable ResNet property? So actually, we can show that. So you can think of the case where, okay, let me go back actually to explain this. So you can think of like a lot of different, scaling sequences that satisfy this property. For example, if you choose this lambda L to be uniform, so lambda L equals 1 over square root of capital L, so 1 over square root of depth. So it naturally satisfies this because this sum will be just equal to 1, right? And it remains bounded. Now, if you think also of a scaling sequence such that this factor lambda small l capital L is equal to some lambda L, so it doesn't depend on depth, but the sum of this lambda L squared is bounded, so meaning that the series converge, right? So in that case, also that scaling sequence satisfies this property, right? So here I'm going to discuss these two cases. One of them is, you can think of this scaling that is decreasing. So I call it decreasing scaling, where this series converge, right? So typically lambda L will converge to 0, right, to have this property satisfied. And the uniform scaling, where all this scalings, actually the scaling factors, are equal to 1 over square root of depth. And the sum of the squares in this case is just equal to 1, and the property is satisfied. So actually we can show that in both cases, the covariance kernel, right? Remember, this is the covariance kernel of the Gaussian process. it converges to some limiting Gaussian process in the limit of infinite depth, right? With some convergence rates that are well characterized. But more importantly, these two kernels, actually this limiting kernels Q infinity hat, are universal in the sense that they are very expressive. Okay, so remember the issue with the MLP was that the correlation converges to 1 and the variance converges to 1, which means that the kernel converges to a constant kernel, right? Now here actually is the opposite. It's really a limit that is universal, meaning that it's very rich. So you can approximate any function with features of this kernel. Okay, right. Okay, this is the first interesting result. So we solved that degeneracy issue with this stable ResNet. Now, another very important result or property of this stable ResNet is that we have stable gradients. So if you use this stable ResNet, so you have stable gradients, meaning that the gradients do not explode and do not vanish. So they remain like of order theta of 1. So they are very well behaved when you increase the depth. Okay, right. So this is just to show you like the results with this stable scaling as compared to without like the usual or the standard implementation that doesn't have any scaling. So here I'm showing the result for CFR10, CFR100, and tiny ImageNet for different depths. Okay, so this is like the standard ResNet architecture with the convolutional layers, So I have depth 3, 32, 50, and 104. So here I'm showing the results for the stable ResNet with the decreasing scaling, with the uniform scaling. And here it's the unscaled ResNet, so without any scaling, but I'm using batch norm. So I'm using batch norm because without batch norm, in most cases, this ResNet will not train because you have this gradient exploding issue, right? Okay. So in order to solve that problem in practice, like practitioners will, introduce this normalization layers to solve that issue. So one of them is batch norm, for example. Okay. But the important thing is that if you just use the scaled ResNet, like either with decreasing or the uniform scaling, you get generally very competitive, if not better, performance as using the standard ResNet with batch norm. Okay, so here I'm not using batch norm. Okay, so this is a major improvement in the cost of training, because batch norm is memory heavy, actually, so it consumes a lot of memory. Right. Okay. Right. So this is basically the empirical verification of this stable scaling. But you might also tell me, okay, so we studied actually all the theory was based on the fact that we take the depth to infinity for the width to infinity first, then look at what happens when we take the depth to infinity. Okay. But in practice, like for example, the standard ResNets, the depth is not much larger than, the width is not much larger than depth. So typically you have like, let's say a width of 64 or 100. And then, for example, for ResNet 104, you have depth of 104 or more than that, etc. Okay, so they are typically of the same order, right? If not, for example, depth is bigger than width, right? So this, naturally raises this question of what happens in the opposite case where depth is much bigger than width. Do we have this stable kind of behavior also in this case, right? So the only way or the only thing we proved so far is that if you take the width to infinity and you take the depth to infinity, you have this stable behavior. The features are stable, the gradients are stable, etc., etc. Okay, so now we want to understand what happens in this case where you can think of depth as much bigger than width. And for example, consider this scaling, this stable ResNet with 1/squared of depth. Does it stabilize the network in this case? So empirically, and this is what we show here, it does, right? So it stabilizes, for example, for 104, it does stabilize the network in this case. Okay, so in order to understand this theoretically, we should consider remember the third limit, the third infinite depth limit, where we have a fixed width, and then we take the depth to infinity. In this case, will give us insights where the width is fixed and then depth is much larger than width. one important thing here is that we no longer have the Gaussian behavior. Remember the Gaussian behavior is just a result of taking the weights to infinity. Everything becomes Gaussian, and that's it. So we study only the kernel. So here we don't have this Gaussian behavior, which means we don't have any kernel, or not studying kernels, right? But there is a very like interesting observation here is that if you consider this simple like stable ResNet with fully connected layers, and you initialize the weights, right, you know, like this. Oh, the same thing with 1 over. Actually, here we can just use any variance here. It doesn't matter. Okay. If you initialize the weights like this with Gaussians, then one observation is that this thing, like this ResNet, looks like an Euler scheme or discretization scheme of a diffusion process. Okay? It's like you think of it as a stochastic or a discretization of a stochastic differential equation. Actually, it has been proven, or we can show this. Actually, it's easy that if the activation function phi is Lipschitz, right, verified, which is satisfied by most activation functions, then if you fix the width and then take depth to infinity, then this process, right, YL evaluated or with index T capital L, it converges in distribution to the solution of this stochastic differential equation. And actually, there are a lot of results on this kind of SDEs that, for example, say that everything here is stable. So XT doesn't explode. It's really bounded in time. So here you can think of basically T going from 0 to 1 as, like you are basically like going through all the layers, right? So because if you take T to be 0, that will be Y0, the first layer. If you take T to be 1, that will be the last layer. Okay, so taking like different values for T will basically mean like different layers in this infinite depth limit. Okay, so yeah, so the result basically means that says that this stability holds even for fixed n and a large depth L. So this scaling is also good for this kind of like fixed width, infinite depth, or large depth in neural networks. Okay, so for those of you who are interested in this kind of results, so I invite you to check these papers. They contain most of what I talked about. Okay, and that will be it for me. Thank you. So if you have any questions, you can ask.
Yeah, thank you very much. Thank you. Any questions or comments?
Is it easy to compute this edge of chaos for new activation functions?
Oh yeah. So is your question how to compute the edge of chaos?
Like the sigma W and sigma B.
Yeah. So it's really easy actually. We have an algorithm. So if you check this paper here on the impacts of the activation function, so we provide an algorithm to exactly compute that edge of chaos for any activation function.
Cool. Thank you.
Sure.
Other questions? Yeah, it seems not. Okay, thanks again for the nice talk.
All right, thanks. Thank you. Thank you.
Yeah, thanks everyone for coming. Yeah, thank you very much. Thank you.
Thank you. Yeah, let me know when you come to Singapore.
Yeah, I'll send you an email. Yeah, thank you very much. Thank you.
All right. See you.
See you. Bye. Bye.